Quarks and antiquarks. Protons, neutrons, and many other particles are made of more fundamental particles called quarks and antiquarks, the antimatter equivalent of quarks. A quark and an antiquark can form a bound state with a variety of different energy levels, each of which corresponds to a different particle observed in the laboratory. As an example, the psi particle is a low-energy bound state of a so-called charm quark and its antiquark with a rest energy of 3097 megaelectron-volts. The psi-2s particle is an excited state of the same quark-antiquark combination with a rest energy of 3686 megaelectron-volts. A simplified representation of the potential energy of interaction between a quark and an antiquark is position-dependent potential energy is equal to amplitude A times absolute value of x, where A is a positive constant and x represents the distance between the quark and the antiquark. You can use the WKB approximation to determine the bound state energy levels for this potential energy function. In the WKB approximation, the energy levels are solutions to this equation, where E is the energy, U of x is the potential energy function, and x equals A and B are the classical turning points, the points at which E is equal to the potential energy, so the Newtonian kinetic energy would be zero. Part A, determine the classical turning points for the potential energy U of x is equal to A times absolute value of x and for an energy E. Alright. Now we're going to require that the position-dependent potential energy, which is a constant A times absolute value of x position, is equal to the total energy, the kinetic energy is zero, which will tell us that there are two possible candidates for x, plus or minus the energy, total energy E divided by A. These are the classical turning points. Okay. Now let's move on to part B of the problem. Carry out the above integral and show that the allowed energy levels in the WKB approximation are given by 1 over 2m parenthesis 3mAh over 4 to the power 2/3 and to the power 2/3 and is 1, 2, 3 an integer. Hint, the integrand is even, so the integral from minus x to plus x is equal to twice the integral from 0 to x. Now I'm going to write the WKB expression, integral between the turning points a, b, square root of 2m square brackets e minus u of x dx is equal to an integer number times Planck's constant divided by 2, where this integer is 1, 2, 3, etc. And we're substituting for the potential energy A times absolute value of x, and for the turning points minus E divided by A and plus E divided by A. 2m E minus A absolute value of x inside the square root dx, and this is going to be equal to twice the integral from 0 to the turning point e over a, because the integrand is an even function. F of x is equal to f of minus x. So this is square root of 2m. If we're only considering positive values, then we have a times x. E minus AX inside the square root dx. And this must be equal to NH over 2 according to WKB approximation. Okay, so we're going to set 2m times E minus AX equal to y squared. So with that, we will have, if we take the differential form of both sides, minus 2ma dx is equal to 2y dy. The 2's will cancel out. And we will find that dx should be written as, with this transformation, minus y dy divided by ma. And when x is equal to the turning point, e over a, y is equal to 0. When x is equal to 0, y is equal to square root of 2m e. All right. So now we're going to rewrite this integral with this transformation. So twice the integral, so 2 times the integral. For dx, we're substituting minus 1 over ma y dy. So minus 1 over ma comes out of the integral. Integral, when x is equal to 0, y is square root 2me. When x is equal to e over a, y is equal to 0, y squared dy. This is rather simple. It is 2 over ma y cubed over 3, and the minus sign changes the order so that I have 0 to square root 2me. So I've operated the minus sign on the integration limits, changed the order. And that gives me 2 over 3ma y to 2me to the power 3 over 2. And this must be equal to nh over 2 according to WKB approximation. So this tells me that I will have the energy given by, so you can see this 2 goes downstairs, so it will become nh over 4, and 3 goes upstairs. So I will have 3 energy is equal to 3 over 4 m a and h to the power, here to the power 2 over 3 divided by 2m. So this is 2me, which is obtained by taking the power to 2 over 3 of both sides, and that's what I obtained for the energy. And this gives me my final answer for the energy levels. Energy is equal to 3m a h divided by 4 to the power 2 over 3, and then I have n to the power 2 over 3 divided by 2m. That's my final answer for the energy levels for the quark-antiquark combination. Part C. Does the difference in energy between successive levels increase, decrease, or remain the same as n increases? How does this compare to the behavior of the energy levels for the harmonic oscillator? For the particle in a box, can you suggest a simple rule that relates the difference in energy between successive levels to the shape of the potential energy function? Okay, so let's summarize our observations. The energy levels are varying with n as n to the power 2/3 when the potential energy function is a linear function of x. The energy levels are proportional to n squared when the potential energy function is a step function, which is the situation in particle in a box. And the energy levels vary as linearly with n when the potential energy function varies as a quadratic function of x, which is the situation in the harmonic oscillator. Okay, so if I change the value of n equals 1 to n equals 2. In the first case, I will obtain 2 to the power 2/3 minus 1 to the power 2/3, which is 1.587. In the second case, it will be 2 to 2 minus 1 to 2, which is 3. In the third case, it will be 2 minus 1, which is 1. If I try n equals 2 to n equals 3, transition, for example, this is 3 to the power 2/3 minus 2 to the power 2/3, 0.492. 3 to the power 2 minus 2 to the power 2, which is 5. 3 minus 2, which is 1. So, what do we observe? The difference in the energy levels does not change for increasing n for a parabolic potential. For this case, harmonic oscillator, the separation between energy levels is a constant. It doesn't change with increasing value of n. For the case of the quark-antiquark combination, which is the first case, you can see that the separation is decreasing between consecutive energy levels. So delta E decreases with increasing n for a linear potential, the quark-antiquark case. And for the particle in a box, where we have a quadratic dependence on n, actually delta E increases with increasing values of n for a step potential. So let's write a general rule. So if the potential energy as a function of x is proportional to x to the power n, x to the power m, okay, the separation between the energy levels increases as n increases if you can see m is greater than 2. The separation between the energy levels stays the same. It's constant when n increases if m is equal to 2. And the separation between the energy levels decreases as n increases if m is less than 2. So m is greater than 2 corresponds to particle in a box situation where we have a step function for the potential. M is equal to 2 is the harmonic oscillator, m is equal to 1, which is m less than 2, corresponds to the quark-antiquark situation. So we can write this general rule. So in this problem, the potential energy profile for quark-antiquark configuration is given by a linear function of x, a absolute value of x. We determined the turning points when the potential energy is equal to the total energy. Then we used the WKB approximation to solve for the energy levels and found that it's proportional to n to the power 2/3. So when the potential energy is a linear function of x, it's n to 2/3. When it is a quadratic function of x, it's n. When it's a step function, as in the particle in a box, it's n squared. So we can see that if we try just a few n values here, delta E seems to be decreasing for the linear function of x. It seems to be increasing for the quadratic function, for the step function, the particle in a box, which means m is much greater than 2 here. If m is equal to 2, x to m is equal to 2, that's the harmonic oscillator, then we have this linear dependence on n, and delta E stays the same. It doesn't change. So that's what we find when we summarize these results.